All right. So we're going to go over 1.4 in Desmos. And we're just going to go slide by slide and make sure that we all understand. So the very first slide says we're going to be able to model a stored context with table, graph, and equation. That's important. You're going to identify features of a function from a graph. And are all quadratic functions increasing? Are all quadratic functions discrete? Okay, we have not really talked about this word. It'll come up today. And then you'll understand what a discrete function is versus a continuous function. So we'll talk about that in a bit. So here's the very first problem, and it matches right here. It says, Misha has a new rabbit that she has named Waskel. She wants to build Waskel a pen so that the rabbit has space to move around safely. Misha has purchased a 72-foot roll of fencing to build a rectangular pen. So imagine it's going all the way around the area where Waskel is going to be. If Misha uses the whole roll of fencing, what are some of the possible dimensions of the pen? So I was looking through here and I saw some really, really good answers. This person says, if Misha uses 72-foot rolling a fence, basically it's 36 plus 36, right? Would be 72. So maybe a possible pen would be 18. And I think they mean 18 by 18, right? 18 by 18. And she says, because the 36 divided by 2 is 18. So that's perfect. Perfect response. If I was going to grade this person, if this was a quiz, I'd probably give this person most of the points. Right. The only reason is they asked for a couple of different dimensions. So if this person puts like maybe one more, that's fine. Someone put 21 by 15. That's another good one. How can you tell? Based on what this person explained, right? They said 72 divided by 2 is 36 plus 36. So then if you look, 21 plus 15 is 36. Okay, this person says basically an 18 by 18, very good. This person said 18 by 18. We got more 18 by 18, it's 18 by 18, very good. So there's other ones. It doesn't have to be 18 by 18. It could literally be 10 by 26 because a 10 by 26 is going to be a complete rectangle, right? Very good, very good. Give me a second. Okay, so then when I'm thinking about alternative dimensions, in reality, based on this person's explanation, really strong explanation, by the way, I just have to make sure that these two numbers add up to 36, right? Because they talked about a rectangle. And if you remember the formula for the perimeter of a rectangle, it's 2 times L plus 2 times W, right? Okay, so it could be 10 by 20, it could be 10 by 26. You guys all said 18 by 18. Apparently you guys like squares, which is nice. You could have even did 16 by 20. A lot of options here. Weird fence, a weird rectangular fence would be 1 by 35. Maybe they just had like that strip of the side of the house that the bunny can run around in, kind of thing. I don't know. So there's a lot of different options. So so hopefully that makes sense. The next one says, if Misha wants a pen with the largest possible area, what dimension should you use? Justify your answer if you need to use a table or graph. Okay, so this person says 18 would give you the area of 324. Oh, that's pretty big. See if anybody, so largest possible area. Okay, so this person said 19 by 17. They got 323, but this person says 324 is bigger. So whoever this is, just put at the very top 18 by 18. Oh, but this person explains we could go 18 by 18, but that would be a square pen, not a rectangle. So technically, I'm going to tell you this, and I told one of my students this, and it was so cute how he responded. So technically, every square is a rectangle. Okay, every square is a rectangle, and I can prove that, right? Because the definition of rectangle is it's a quadrilateral. That means it has 4 sides. And a rectangle means that the angles are right angles or 90-degree angles, which that's what a square is. A square has 4 sides and it has right angles, except for a square has one extra little constraint, which is the square will have 4 congruent sides. Okay, so this person explains it really, really well. I would just at the very, very top, just put 18 by 18 actually would be a bigger thing. And you could leave all this here. Very good, because this shows your process. I like it. So 19 by 17, nope, it's actually 324. Very good. I like how this person is proving it by they showed a couple others there. Very good. They used a table. Very good. Awesome. So here our answer is going to be 18 by 18 equals 324 square feet of space, right? You can use a table to show that or whatever. Let's see, what else did I want to say? Okay, the next one says, write a model for the area of the rectangular pen in terms of the length of one side. Include both an equation and a graph. Okay, so this one I could see we definitely did need help on. People asked about this slide as well, so very, very good. I'm going to write it right here. I'm going to actually ignore this right here, so don't worry about that. It says write a model for the area. Okay, so I'm going to start with that because a lot of students think, Ms. Johnson, I don't know how to write the model for the area. But you do know how to find the area of a rectangle, right? So let's start right there. And I'm going to write down here, what's the area? And then can you please put this in the chat? What's the area formula of a rectangle? How do you find the area of a rectangle? What is that? What's the area of a rectangle? Nice. Length times width. Exactly. Length times width. Very good. I know what you meant. You're good. Okay, so that technically is the area of a rectangle, but then it says in terms of, and I'll get this a little bit bigger so you can actually see what it says. It says in terms of the length of one side, in terms of the length of one side. Oh no, I have width here. So I want to almost get rid of that W so that it just says L. Whenever it says stuff like this, when it says in terms of length, that means the only other variable in your function should be length. Does that make sense? So I shouldn't have this W. So over here, I'm going to circle this W like, oh no, it should only be length. Does that make sense? So I need to figure out, how do I find this W? Well, you guys already figured this out, right? If I know one of the lengths, can I find the width? If I know the length, would I be able to find the length? And you guys should all come back with, yeah, I think so. So does anybody know if I know the length, if I told you, okay, I want to go back over here and I want to say the number 15. If 15 was my length, would you be able to find my width? And if you say yes, how you found it is the formula that I need right here. So if you know that the length is 15, how would you find your width? Anybody in the chat? All right, right? Yes. No, not by subtracting the area, but by subtracting it from what? What would it be? Actually, can you pause right there? What would it be? If this was 15 for the length, what would the width have to be in order to do this? What would the width have to be? Exactly, Nathan. Nathan says, Ms. Johnson, it would be 36 minus 15. And if you look, that's exactly how I got this 35. I did 36 minus 1. I did 36 minus 16. So it's just 36 minus 15. And I'm literally going to write it like this because I like how he wrote it. Okay, so I'm going to write it like that. Okay, fine. If that makes sense, if I can find the width based on the length, then what if my length was L? If my length is L, what would my width be? If my length is L, what would my width be? Okay, if my length was 15, Nathan said, Ms. Johnson, it's 36 minus 15. Very good. But if it's L, what would it be? Give me a guess. If you don't know, it's okay. Just give me a guess. Give me a I don't know. Give me a something. I need a couple more people's responses, guys. Come on, y'all. Yeah, in this case, it would be 21. It would be 21. But in this case, if the length I'm using is L, what would this in here be? So I'm going to do this. If this was L, if that was an L instead of 15, then this wouldn't be 36 minus 15. This would be 36 minus L, right? Does that make sense? Oops. It would just be 36 minus L. Does that make sense? Can you put that in the chat? L times 36 minus L. I just need you to put that in the chat. The reason why I want that in the chat is because if I make you write that in class, I would have made you like say it out loud. Okay, everybody turn to your neighbor, say 36 minus L, right? Very good, very, very good. Now, the reason why this is true is because of the formula of perimeter. So a long time ago, I think in like fourth grade-ish, it wasn't this formula, but this is how you found it. It's perimeter equals to 2W plus 2L. Now, if you solve for W, this is like back in 8th grade-ish, right? You would subtract 2L from both sides. We go P minus 2L equals 2W. And then we would divide each side by 2, right? And then so W equals to P over 2 minus 2L. But in this case, they told you that P was 72. That's our perimeter, right? So over here, I'm just going to rewrite this for 72, and I get 72 divided by 2 minus 2L over 2, sorry, with minus L, which that's just 36, which is exactly what Nathan told us. So if you're the type of student that you're like, ugh, it's variables, Miss Johnson, don't make me think in variables. You are already thinking in variables. You just thought of this specific case, right? So it's okay to put 36 minus L because you already knew that. Nathan told us 36 minus 15. What's 15, Miss Johnson? Well, that was our L. Oh, okay. So down here, I'm going to be writing 36 minus L. Okay. So this is the area formula that they wanted. Yeah, let me check. Write a model for the area, check its area, of the rectangular pin, yep, length times width, in terms of length. So the only thing that I should see here is L, 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 L. Very good, very good. L, L. I only have L's. Ms. Johnson, why couldn't we use the W? Because they told us not to, only in terms of length. Okay. So I'm gonna multiply this out because it looks a little funny to me right now. So this is 36L minus L squared. Now, the moment that I wrote L squared, right, your brain should be like, oh my gosh, I know the shape of this thing. Miss Johnson has been talking about the shape of this thing. Okay, so let's talk about the shape of this thing. So we go to Desmos, clear this out from earlier. And I'm going to graph this formula right here, which is 36L minus L squared. Okay, so Y equals 36, and I'm going to use X because Desmos likes X. And we'll listen to Desmos because Desmos is this. Okay, everybody good? And you're looking at it and you're like, Ms. Johnson, it looks like a line. Kind of. So I'm going to zoom out a little bit just so that we can look at more of the curve. It's not, right? You guys all see this. This is not a line. Like when we zoomed in, right? Doesn't this look line-ish? Right? Kind of looks line-ish, but then when we zoom out, you'll see that it's actually a parabola. Everybody say parabola. Put it in the chat. Parabola, Miss Johnson, that's a parabola. You're right. His name is Parabola. Parabolas, you should be saying thank you to parabolas. Parabolas are really good for you. For those of you who have a cell phone, this is kind of what we use. If you ever looked at a satellite dish, that's the shape. It's a parabola. Parabola. Yay, parabolas. Yes, exactly. Oh, it's right here. I'm sorry. I'm not saying it clearly. Parabola. Parabola. Let's see, what else do I want to show you? So then I would get this graph here. It doesn't have to be perfect. I'm not looking for a perfect graph, so I'm just going to go like that. Good. And then I'm just going to get some of these features on here. I'm going to say this is 0, 0 right here. Right. And this part here, I'm going to point at this part here. Important features of a parabola are always going to be the x-intercepts, meaning where it crashes into the x-axis. So I'm going to graph this point here too. Right. And then the other one is the tippy top or the lowest bottom. So that guy right there. So 18, 324. Wait a second. I remember that 18,324. Shoot. Who? Someone was telling me about 18,324. Yeah, you guys all should remember this, right? From the previous slide, you guys all told me that the biggest area for my little wascally wabbit is going to be 18 by 18, and it's going to be 324. It's Johnson. It's all connecting. That's right. That's right. It's all connecting, right? It's all connecting. So let's continue on. So you should be that. Yeah, the drawing doesn't have to be perfect. Look, this is a perfect graph right here, whoever this person is. That's beautiful. Just give me some points right here. Like give me this one as a point right here, just so that we know where you're pointing to. Does that make sense? So just keep that in mind. Just give me points like this, like this. This would be really good. Let's see, write a model for the graph. So this is incorrect. You need to write this over there, right? This next part, what kind of function is this? Okay, let's see. Did anybody put this answer yet? Yes, it's a quadratic function. Muy bien, it is a quadratic function. It's not linear. No, this does not look like a line. Yes, this person even better, quadratic because of the x squared. Can you guys put some of those answers in your answer? Is this, let's see, x squared, very good. Yeah, very, very good. Okay, so I'm going to write that quadratic. And then someone said because x squared. In this case, it's L squared, but you guys all know what we're talking about. Very good. It's a quadratic. It's a quadratic. So remember all the quadratics that we've dealt with so far. Think about, I keep remembering Jade's I, and it was like 7n squared, right? Because she kept seeing those squares over and over again. Okay, how does this function compare to the I rule function? And that's what we were just talking about a second ago. This is talking about Jade's function of 7n squared. So I'm actually going to graph both of them, and then you're going to tell me what you think. Y equals 7x to the second. Okay, how are these two graphs? What does it say? Different? Shoot. How does it compare? So how are these the same? Very good. They're both quadratic. Let me take notes on this so that you guys can grab some answers. So number one, they're both quadratic. Very good. Let me use a different color. Both quadratic. Very good. Very, very good. What else? Very good. They're both quadratic. Good. Now, whenever they tell you to compare something, like if I said, I need you to compare, let's see, what would be a good compare? In-N-Out to McDonald's. No problem. Have a great day. Okay. I need you to compare In-N-Out to McDonald's. In-N-Out to McDonald's, right? You'd be like, they're both burger places. Yes, very good, Jade. They both serve burgers. They both serve. Now tell me about the differences between them. Now you guys can be like really explicit, right? Like, exactly. Nathan says animal style. That doesn't exist in McDonald's land. In-N-Out is way better. I agree. I agree. Not only in quality, but in service as well. Like I've never had a bad In-N-Out. Yes, Robert, that's what I was just going to talk about. They're more consistent. Yes, Evan, I'm with you. They're healthier. I agree. I agree with all these things. And In-N-Out gives kids free hot chocolate when it's raining outside. Did you know that? No, you didn't. I just taught you something. You're welcome. It's not great hot chocolate. I don't think like it's going to be amazing, but it is free. So that's really cool. Okay. Sounds good. Thank you for letting me know, hon. McDonald's ice cream machine is always broken. Okay. You guys are hilarious. Okay. So with that being said, can you tell me some of the differences here? Now I'm going to zoom in a little bit, just so you guys can see. I don't know if you can tell, but this blue function right here is really skinny right there, right? What does that mean? What does In-N-Out is mid? It's like,
Basically saying disgusting.
oh, really? No way. I love In-N-Out. I know. Okay, sorry. Okay, right here. So how are these two different then? How are these two different? Now I'm gonna change my little settings here just so you can, like, I just want to open this up just a little bit. So I want to go from probably, I don't know, -10 to +36. Okay, that's better. Okay, so I wanted to open it up a little just so you can see the curves a little bit better. What's different? Yes, Nathan says one is opening up, the other one's opening down. Very good. Now here, what I like to do is when I find a difference like that, I like to say like, hey, equation. What? Okay, so green is opening down. What in the green equation is making you open down? And then, hey, blue equation, what in the blue equation is making it open up? Okay, so I'm going to write that down. Hold on a second. One opens up, and then the other opens down. So I go like this. I go like this, right? Very good. Oh, yes, Robert. Very good. Yes, Jade. Very good. Both of you are right. Robert said the negative, that negative right there. You guys all see him? He's making the green open down. Very good. Very good. And then subtracting, exactly, Jade. Same thing. That subtraction sign right there, it's a negative. It's making that whole function go upside down. Very, very good. Very, very good. Very, very, very good. Another difference that you guys can look at is this one has a tippy top maximum. That's it. This one has a maximum versus this one has a minimum, meaning the blue function doesn't go below this point and the green function doesn't go above this point. So this one has a minimum and this one has a maximum. Okay, there's other differences that I want to talk about. Jade actually noticed a different thing when she said that subtracting, that actually is a difference. This one has no like plus something. Yes, 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 yes. I will do that. Very good. Let me just make it smaller tab so you can see that too. Yeah, so this one right here is this one right here. Very good. So this, because this has two terms, 1 36x, 2 x squared. They have two terms here. This one only has one. And because this one only has one term, it means something to my graph. You know how like I don't know if you've ever watched like a movie or something and you're like, and then you go like, you think about it and you're like, oh my gosh, every detail like maybe it's a mystery and then you find out something at the very end and then you rewatch it and you're like, oh, that's why they did that, because everything matters towards the end. Same thing goes with functions. Like everything in here made this function do this, right? This is almost like the DNA of this function, right? Everything in this function, 36x minus x squared, made this function look like this, right? Everything, this is basically the DNA of your function, if that makes sense. Very good. There's other differences, but I don't really want to talk about them right now. I just want to make sure that you guys are all set. Let me move on. So you guys should be set with that one. You don't have to write all of them, but make sure that you get a couple of them in there. So very good. Very good. Okay, so now you should understand quadratics. Quadratics, what do quadratics have in common? They all have this squared. Very good, Jade. They all have a squared right here. All of them do. All of them have this shape, like we said. Not all of them are going to open up. Not all of them are going to open down. The other question that they asked us in the very beginning, I want to bring that up. Are all quadratic functions increasing? And so here you can see, Ms. Johnson, it's going up. So yes, and then it goes down here. So the answer here is no, some of them are actually decreasing. This is decreasing here on the right side. Are all quadratic functions discrete? Now discrete here is gonna be talking about this function, or kind of. So discrete just means that, do you remember when we were talking about like this function here, 7n squared? And we're talking about the different stages of it. So for example, like the first one versus the second one, this function here was what we consider discrete from the context, not from that function. Because if we graphed it, it would really look like a bunch of dots like this. This is what discrete means. So discrete means not connected. So if we go back over, how do we do that the quickest way? Let's go here. Give me a second, let me pull it up real quick. I will, here it is. This one. So when we were looking at this, size 1 was this, size 2 was this, size 3 was this, size 4 was this, right? Technically, it shouldn't have a curve, right? We shouldn't have a curve. It should be these dots that are not connected, right? The reason why we can't connect those dots is because I don't have a size 3.5, right? I don't have a size 3.5. I have a size 3, and then next I have a size 4. Right? And I also don't have 2.5 boxes. I only have a clear amount. So I had the 7, and then I had the whatever. Does that make sense? So discrete means it looks like this, disconnected. And this is versus continuous, which same function, right, looks like this. Okay, I actually don't like this arrow right here, so I'm going to erase this. So discrete means they're dot, right? Continuous means that it's a smooth curve like this. So the way I like to tell it to my students is this, right? If we were on a roller coaster and this was the roller coaster track, I'm good with this. Woo! Right? Because it's completely continuous. This one, do you see how we're missing parts of the track? Like not a good roller coaster track. Very good roller coaster track. Does that make sense? So this is discrete. This is continuous. Okay. All right. So technically, I want to make sure we got everything. Go back over here, Miss Johnson. We need to go over here to ready for more. So if the rabbit pen does not need to be rectangular, is there a way to get more than 72 feet Is there a way to get more than 72 feet? And the answer is yes, but I'm not going to tell you the answer. Okay. So I will give you a hint here. This skinny little rectangle right here, the 1 by 35, it's going to be 35 square feet. It's a skinny rectangle versus this one, which is a square, gave much more area, right? So I'm gonna have you explore this so that you guys can think about it. Let me pause right there.